Hello.
Hello, hello.
Yeah. Okay, so we'll begin our class. This is the first question. If A and B are relatively prime, we have to show that A plus B and A minus B are either relatively prime or their GCD is 2. Are you saying something? Can't hear you.
No, I'm talking to myself.
Okay. You can start off by saying that let D be the GCD of
GC
A plus B
A.
and A minus B.
Then I say like let D is an integer greater than 3, and then I show there is some contradiction.
Okay. You could try that, yeah.
Like dark, I cannot proceed on.
So from here, if D is the GCD of this, then you can say that D divides what? A plus B and D divides A minus B. So from here, you should be able to do something.
Then I say like A plus B equals D times K1.
That you can say.
And like a minus b is d times k2.
Hmm.
Then 2a equals d times k1 plus k2, and 2b equals d
Hmm.
times k1 minus k2.
Correct. So something like this you will get, and 2b equals t times k1 minus k2.
Yeah, then I don't know how to proceed.
Then you can say that basically you get d divides 2a and d divides 2b, right?
Yeah,
This you are getting. So, so what is the GCD of 2a and 2b?
2 and 2b 2.
Is 2 because uh, a and b are relatively prime, right?
Yeah,
So if d divides 2a, d divides 2b, then d is a factor, right, of both.
yeah,
And GCD of them is 2. GCD is greatest common divisor, right?
yeah.
So then d must divide 2, right?
Oh yeah, so d is either 1 or 2.
Yeah. So d can be either 1 or 2 because d is a divisor and the greatest common divisor is 2, right?
Oh
Correct.
yeah, I didn't notice.
Yeah. So till here you can do like d divides 2a, d divides 2b from here. And then you can say that, okay, because a and b are relatively prime, the GCD of 2a and 2b is 2. And d is one of the divisors. So d must divide 2, right?
Yeah,
Okay. Uh, let's look at the next one, which is if GCD of A and B is 1, then show that GCD of A plus minus B comma B is 1 and GCD of A plus minus B is also 1. This is similar to what we did yesterday, last class.
uh, this one I did after the
Yeah,
previous class.
yeah. So this should be easy. You just do the,
Yeah,
uh, you can assume GCD of this is D, and then you have to prove that D is 1, right?
yeah, yeah,
So you can say from here that if GCD of this is D, then D divides A plus minus B and D divides B,
yeah,
right? This implies since D divides B, D also must divide A, right? From here and here, right?
yeah,
D must divide A. So then D is a divisor of D must divide both A and D must divide B. So D is a divisor of both. And GCD of A and B is 1, so D is 1, right?
yeah,
So this is fairly easy. So we won't you understood, no? This is fine, right?
yeah. I did this like several days ago.
Yeah, yeah. Okay. So the next one is this one. Uh, prove that the fraction, prove that the fraction 21n plus 4 divided by 14n plus 3 is irreducible, irreducible for any natural number n. What do we mean by irreducible?
Like for any n, this is not an integer.
Irreducible fraction means you cannot take anything more common out of it. Like
Oh,
2 by 4, you could have taken made it 1 by 2, right?
oh yeah. So I should show that
Hmm.
these two has no like kind of a common
Basically,
factor.
basically you have to show that 21n plus 4 and 14n plus 3, their GCD should be 1,
Okay.
right?
Oh, so this is the like the Bezos identity.
This is like Bezos identity, yeah. So if their GCD was D, you could have proved that D should be equal to some x times 21n plus 4 plus some y times 14n plus 3. In this case, D is 1, so you have to show this. Is there an integer x and an integer y such that this happens, right?
Yeah.
This is like Bezoart's
So
identity.
so I let x be 2
X
and
be
the
minus
y,
2 and y be 3, right?
yeah.
3 makes it 42 and 42 cancels, and 9 minus 8 is 1, right?
So this is enough.
Yeah, this is enough. If you show this, if you realize that 3 into this minus 2 into this is 1, that is Bezoart's identity. And now you prove that basically this GCD is 1. And if this GCD is 1, you cannot take any common factor out of it, right?
Yeah.
So the fraction becomes irreducible.
Yeah.
Okay. Now let's move on to some theory. And for example, we'll start talking about prime numbers now. So the definition of prime numbers, obviously, you know, prime numbers are those which have only two factors, themselves and one, right?
Yeah.
No other factors, no other factors except one and p itself. Those numbers are known as prime numbers. Now, what we will say, the first thing that we learn is Euclid's theorem, which says that the number of primes is infinite. The number of primes is infinite. Do you know the proof of this one? This is very nice proof.
I think I've heard it's like
Uh,
if if the number is finite, then I
uh,
times everything. Then I multiply every prime
uh,
number.
plus
Then
one.
yeah, plus one.
So basically, it's a proof by contradiction. The way you do the proof is say ki, okay, assume number of primes is finite. Assume the number of primes is finite, and then you make a list of those primes. And let's say the list is like this: P1, P2 till Pn, right? And then you construct a new number, capital X, which is P1 into P2 till Pn plus 1, right? Now you can show that X is not divisible by any of the prime numbers, by P1, P2 till Pn. So that means that since it is not divisible by any prime number, the only thing it is divisible by is 1 and X. So X is also a prime, right?
Yeah.
And if X is also a prime, that means it should be added to this set. That means this is not the complete set and there is a contradiction, right?
Yeah.
Once you add it to this set, you can construct a new prime number by including X here, right?
Yeah.
So the
And then
process
there's
can be repeated, correct?
yeah.
So you will get infinite primes in that way, right?
Yeah.
So this is a nice proof that number of primes is infinite. Now, we will see more theory, but we'll first do a couple of questions. We'll say, prove that if P and 8P minus 1 are prime, then 8P plus 1 is a composite number. Any number that is not a prime is a composite number.
Yeah.
slightly tricky this one is. Think of the numbers 8p minus 1, 8p, and 8p plus 1.
I have no idea.
See, think of these three numbers. 8p minus 1, 8p, these are three consecutive numbers, no?
Yeah.
So if there are three consecutive numbers, one of them is divisible by 3, right?
Yeah.
Okay. One of them is divisible by 3. So now, if you look at 8p minus 1, they have said that 8p minus 1 is prime, right?
Yeah.
So that can't be divisible by 3, right?
Yeah.
Okay. So out of these two, one of them is divisible by 3, correct?
Yeah.
So we
Oh,
have, if p is divisible by 3, if p is divisible by 3, then 3 divides 8p, right?
yeah.
But p is a prime, so the only possibility for p must be p is equal to 3, right? If p is
Yeah.
divisible by 3, right? If
Yeah.
p is equal to 3, then 8p plus 1 is equal to 25, right?
Yeah.
Which is composite, correct?
And then if P is not 3,
If
then
p is not 3, then p cannot be divisible by 3 then, right?
then yeah, then 8P plus 1 is divisible by 3.
Correct. P is prime. If p is not 3, p is prime, so p is not divisible by 3, and therefore 8p is not divisible by 3. And therefore both of these are not divisible by 3, so 8p plus 1 must be divisible by 3, right?
Yeah.
That makes 8p plus 1 composite again, right?
Yeah.
So basically there are two cases here. You have to realize that in these three numbers, one of them has to be divisible by 3, 8p minus 1 is prime, cannot be divisible by 3. And now you think about 8p and 8p plus 1. 8p can be divisible by 3 only if p is equal to 3, in which case 8p plus 1 is composite. And if 8p is not divisible by 3, that means p is not divisible by 3. And then 8p plus 1 becomes divisible by 3, which means it is again composite. Right?
Yeah.
So a little
Yeah.
tricky, but once you get the idea, then it is not so hard also. Right?
Yeah.
Okay. Look at this one. Prove that the polynomial f of x is equal to x power 4 plus 26x cube plus 52x square plus 78x plus 1989 cannot be expressed as a product of two polynomials p of x and q of x, p of x and q of x with integer coefficients with integer coefficients and of degree less than 4. Degree less than 4. Basically, he's saying that you have to prove that fx will never be equal to px multiplied by qx, where px and qx are product of two polynomials with degree less than 4 having integer coefficients,
Okay.
right?
Yeah.
So there are multiple options for px and qx. Like how would you arrange px and qx to get a fourth degree polynomial here, right? You can get degree 2 and degree 2, right?
Degree 3 and degree 1.
Or you can do degree 3 and degree 1, right? These are the options, right?
Yeah.
So you have to think about both those cases. So start thinking about, like, let's say case 1 where fx is written as px multiplied by qx, where both of them px and qx are degree 1, degree 2, right?
Yeah.
You have to prove that this is not possible. Fx is already given to you. You should take two quadratic polynomials here. So you can assume first one is x square plus ax plus b, and the second one is x square plus cx plus d, right?
Yeah.
Why am I not assuming some number here? Because the first degree is 1 here, right? So you
Yeah.
cannot have any constant 2x square or something here, right?
Yeah.
Here a, b, c, d are integers, that is given, right?
Yeah.
So now, obviously, if fx is equal to this, then all the coefficients must match, right?
Yeah.
After multiplying, all the coefficients should match, correct?
Yeah.
So what is the x cube coefficient when we multiply these two? You will get x squared
A plus.
c plus a, right?
Yeah.
C plus a should be 26, right?
Yeah.
What is the x square term? It will be
AC plus B plus D.
ac plus b plus d should be equal to 52, right?
Yeah.
X term would be
AD plus BC.
AD plus BC should be 78. And finally, BD should be equal to 1989, right?
Yeah.
Now, what do we have to show? We have to show that there are no such 4 integers for which these relations can be true, right?
Yeah.
Okay, so let's think of that now. Like you can take some time and think about it, how you would prove that. Before you can do anything, you should prime factorize 1989. One nine eight nine is actually this 3 square into 13 into 17.
So it was like from the last two, from the last one, I
Mhm.
can say that one of B and D is divisible by 13.
Correct. You
Then
can say
from
13 divides B or 13 divides D, but not both.
yeah, yeah, but then from like AD plus BC equals 78.
Uh-huh.
If I mean, if I assume D is divisible by 13, but not B, then
So
AD
take
is
this
divisible by
case. So take this case, 13 does not divide B, right?
yeah, yeah,
So then
but
D is divisible. So this part is divisible by 13,
yeah,
but we don't know
but
anything about C, right?
yeah,
So right now, directly you can't say much. You have to look at this one actually first.
oh, yeah,
Uh, AC. Okay, so okay, wait. You can say 13 divides BC, right? From here.
yeah. No,
Because 13 divides D. So this is divisible by 30 and this is divisible by 13, right?
so I can directly say C is divisible by 13.
So you should say 13 divides C, right?
Yeah, so like C is either 0 or 13 or 26. Eh?
Don't worry about the actual number here. Now look at second one, right?
Yeah,
So far you know 13 divides D, 13 divides C, right? And 13 does not divide B,
yeah,
right? So if 13 divides C, 13 divides AC, 13 divides D, and you're getting 13 divides B then, right?
oh yeah. So this is definitely not true.
So contradiction, right?
Yeah,
And you can do the case 2 also. Case 2 would be just the opposite, right?
yeah,
And similarly, you can prove a contradiction there also, right?
yeah,
Exactly same thing. B and D can be interchanged, right?
yeah,
So we have proved one part, that fx is equal to px and qx is not possible if px and qx are quadratics, right?
yeah,
The other part would be to prove that fx is equal to px and qx is not possible if px has degree 3 and qx has degree 1, right? Correct.
yeah,
So degree 3 polynomial you can take as x cube plus ax square plus bx plus c, right? And qx can be taken as x plus d, right? When you multiply these together, again you will get a set of equations that must be true if it is equal to f of x, right?
yeah,
The first equation, first term, we don't care. The x cube term, you will get a plus d should be equal to 26. X square term, you'll get ad plus b is equal to 52, right?
yeah,
X term would be bd plus c is equal to 78, and finally cd should be equal to 13 into 3 square into 17, right?
so I use the same method.
Same method. You can say from here that 13 should divide CD. So 13 divides C and 13 does not divide D, right?
Yeah,
That is your case 1. Case 2 will be the opposite of that. If 13 divides C and 13 does not divide D, this implies from here that 13 divides B, right?
yeah,
13 divides D, then that means 13 divides AD here, right?
yeah,
That means since it does not divide A, it implies 13 divides A, right?
yeah,
And from first one, that implies 13 divides D, which is a contradiction. Are you understanding?
Yeah.
From here, you get 13 divides A, and from here, you get 13 divides D then, right?
Yeah.
Okay. So again, the notion of divisibility is coming in handy, and we are using that to solve many different kinds of problems. So like this looks like an algebra question, right?
Yeah.
Okay. Then the next one is prove that n power 4 plus 4 is a composite number for all n belong to natural number greater than 1. N greater than 1, n belongs to natural number. This is a very famous thing actually. This is called Sophie Germain's identity. So if you don't know it yet, now by this problem we will know it. This is a actually this is a question where can you factorize this, right?
Oh, yeah.
If you can factorize it, then you'll have it as a product of two different natural numbers, right?
Yeah.
So think about what you can do here. Like this is something square and this is 2 square, right?
Yeah.
So you are just missing the middle term, right? So
Yeah.
you're missing the middle term. So if you added 2 into 2 into n square and subtracted that, right? That would be the same thing, no?
Oh yeah. Then the 2 times 2 times n square is also square. So that is a
Correct.
difference.
This is coming, right?
Yeah.
And now you can do a plus b into a minus b here, a square minus b square. You can write n square plus 2 plus 2n and n square plus 2 minus 2n, right?
Yeah.
So now these are all natural numbers, correct?
Yeah.
So you have
N is,
basically written n power 4 plus 4 as product of two natural numbers,
yeah.
right?
Yeah.
And that is the basic identity. The basic identity, Sophie-Germain identity is this: a power 4 plus 4b power 4 is equal to a square plus 2b square whole square minus 4a square b square, right? Again, you have
Yeah.
added and subtracted plus 4a square b square. And this becomes a square plus 2ab plus 2b square multiplied by a square minus 2ab plus 2b square, right?
Yeah.
Which is a plus b whole square plus b square multiplied by a minus b whole square plus b square, right?
Yeah.
So it may seem like a very obvious thing, but this property and this identity has some uses in questions like this one, for example. We'll say question is this: prove that n power 4 plus 4 power n is a composite number, for all n belongs to natural numbers and n is greater than 1. You can take one case, two cases, and one case is very easy to say. Case one is basically n is even. If n is even, it is obvious, right?
Yeah. It's a even number.
The whole thing is even. So it is composite. The only thing you have to really prove is case 2 when n is odd. So if n is odd, n can be written as 2k plus 1,
Yeah.
right? So you have n power 4 plus 4 power n, and this n can be written as 2k plus 1,
Yeah.
right? And now you will use Sophie-Germain here. How will we use that? You will say n power 4 plus 4 power 2k multiplied by 4 power 1, right?
Yeah.
So n power 4 plus 4 times 4 power 2k. And Sophie-Germain was a power 4 plus 4 b power 4, right?
Yeah.
This was factorized.
Yeah. So like 4 to the power of 2k, 2 times 2 to
Correct.
the power. Okay.
So you can write it as 2 times 4k, right? So
Yeah.
this becomes n power 4 plus 4, 2 power k power 4, right?
Yeah.
Now a is your n and b is your 2 power k, right?
Yeah.
So the factorization of this came out to be a plus b whole square plus b square and a minus b whole square plus b square, right?
Yeah.
So I will do that here also. A plus b will be n plus 2 power k whole square plus b square, so 2 power 2k multiplied by n minus 2 power k whole square plus 2 power 2k, right?
Yeah.
Okay. Now, let's think about what this means. These are now, since n minus 2 power k whole square. See, everything is positive here. No, it's not like anything is negative. So we have basically represented the whole thing as product of two natural numbers, right?
Yeah.
So in this case also it is coming composite, right?
Yeah.
Because it has been written as a product of two integers.
Yeah.
So here we are using the Sophie-Germain identity, correct?
Yeah.
Okay. Then a little theory now. For example, what we'll talk about next is the fundamental theorem of arithmetic. Fundamental theorem of arithmetic. Basically, it says that every natural number or every integer greater than 1 can be expressed as a unique product of primes, can be uniquely expressed as a product of primes, right?
Yeah.
Basically, there is a prime
There is a prime
factorization
factorization.
greater than 1. So any number n can be written as p1 power alpha 1 multiplied by p2 power alpha 2, p3 power alpha 3, and so on for all prime numbers. Your alpha 1, alpha 2, alpha 3 could be 0 or 1 or more, right?
Yeah.
And p1, p2, p3 are basically 2, 3, 5, 7, whatever, right?
Yeah.
Okay. Now, when is a number like this, a number n, going to be a perfect square? Going to be a perfect square only if all the alphas are even, right?
Yeah.
Each alpha is even, then only the number n becomes a perfect square, right?
Yeah.
And if sometimes there is another idea here, another term here, when is n going to be square free? Going to be a square free number. Square free number. That means if each alpha is 1, basically there is not even one alpha which is 2 or more from where you can take a square out, right?
Okay. Yeah.
Like every prime number occurs only once if it occurs. There is not even a single prime number which is present in square or 4 times or 3 times or whatever, right?
Yeah.
Such a number is a square free number. From this prime factorization, we can also find total number of divisors of n.
Is it like alpha?
Total number of divisors of n is called tau of n. There is the same symbol for it, tau of n, and that is equal to, you know, that alpha 1 plus 1 multiplied by alpha 2 plus 1 till alpha
Multiply.
n plus 1, right?
Yeah.
If n is written like this, p1 power alpha 1, p2 power alpha 2 till pn power alpha n, in that case number of divisors are these. Why is this so? Why is this the number of divisors?
Like for P1, I can choose the power to be 0, 1, 2, 3.
2n, 2 alpha 1,
Yeah. Yeah.
right? So there are alpha 1 plus 1 choices for
Yeah.
the p1 prime, and similarly there are alpha 2 plus 1 choices for the p2 prime, right?
Yeah.
Correct, no?
Yeah.
By the way, this tau of n also includes the case when you are saying 1 is a divisor or n itself is a divisor. Because you can choose 0, 0, 0 in all the brackets, and then you'll
Yeah.
get the number 1. And you can also choose alpha 1, alpha 2, alpha n in all the brackets, and you'll get the number n itself,
Yeah.
right? Okay. If n is a perfect square, then tau of n will be odd, right?
Yeah.
Because n is a perfect square means each alpha is even. So alpha
Yeah. So,
plus 1, all of them are odd, right?
yeah.
If n is not a perfect square, then there will be at least one of them which will be odd, which will make alpha 1 plus 1 even, right?
Yeah.
Tau of n will be even. So from knowing the value of tau of n, you can decide whether it is a perfect square or not, right? You can say
Yeah.
that tau of n will be odd only if it is a perfect square.
Yeah.
Right?
Yeah.
Okay. Now you can even find the sum of all possible divisors from here. Like if someone asked you, okay, tau of n is telling you total number of divisors, right? You can also find what is the sum of all possible divisors. And that is written by sigma of n. That is written as sigma of n. Okay. And
Yeah.
that will be equal to, we will show you how. It will be equal to P1 alpha 1 plus 1 minus 1 by P1 minus 1. P2 alpha 2 plus 1 minus 1 by P2 minus 1. And so on. You'll keep doing this till Pn alpha n plus 1 minus 1 by Pn minus 1. Here n was what? N was P1 alpha 1, P2 alpha 2, and so on till Pn alpha n. Right?
Yeah.
Now, how is this happening? This is happening because, like, we can take an example and understand these are all sums of GPs. It's a geometric progression. Have you heard of geometric progression?
Yeah. Yeah. Yeah.
Okay. So if you have a geometric progression like this, 1 plus P1 square till P1 power alpha 1, right?
Yeah.
Then the sum of that would be P1 power, there are actually alpha 1 plus 1 terms here. So P1 alpha 1 plus 1 minus 1 by common ratio is P1. So P1 minus 1, right?
Yeah.
So that is what is happening here. How are we getting that? So take an example. Let's say your n is 24, right? 24
Yeah.
is actually equal to 2 power 3 into 3 power 1, right?
Yeah.
Correct. So let's write down the possible divisors of 24. Divisors would be 2 power 0 into 3 power 0, right? 2 power 1 into 3 power 0, 2 power 2 into 3 power 0, 2 power 3 into 3 power 0, right? And
Yeah.
then there would also be 2 power 0 into 3 power 1, 2 power 1 into 3 power 1, 2 power 2 into 3 power 1, and 2 power 3 into 3 power 1, right?
Yeah.
There is no other possibility, right?
Yeah.
2 powers have gone from 0 to 3, and 3 powers have gone from 0 to 1, right?
Yeah.
These are all the divisors, and I want to add all of them to find sum of all the divisors. So now add in a vertical column like this. Add like this. Take 3 power 0 common, right?
Yeah.
3 power 0 common. This is 2 power 0 plus 2 power 1 plus 2 power 2 plus 2 power 3, which is like this, right? Like this.
Oh, yeah.
And that will be basically 2 power 4 minus 1 by 2 minus 1, right?
Yeah.
And then again take 3 power 1 common like this. So 3 power 1, and again this is the same thing. So it will be 2 power 4 minus 1 by 2 minus 1, right?
Yeah.
And then take this common. You get 2 power 4 minus 1 by 2 minus 1 multiplied by 3 power 0 plus 3 power 1, which will be 3 power 2 minus 1 by 3 minus 1, right?
Yeah.
Are you understanding what we are doing?
Yeah.
We are writing all the possible divisors and we are adding vertically so that we can add all the divisors of two increasing powers once and then take common the 3 power, right?
Yeah.
In the same way, you can prove if it was more complicated, you can prove this also. Basically, keep everything else fixed, vary p powers from 0 to alpha 1, right?
Yeah.
Then keep everything else fixed, vary p2 powers from 0 to alpha 2, something like that.
Yeah.
And add in a vertical column. Okay.
Yeah.
You can convince yourself that this formula will work. This will give you the sum of all possible divisors. Correct?
Yeah.
Okay. Now let's look at some questions which use the concepts that we have seen so far. So this question is, find the smallest integer. Find the smallest integer with exactly 24 divisors. Saw this question, no? Smallest integer, exactly.
So are you saying something? I cannot hear.
You can't hear me right now. Hello, hello.
Wait, no, no, I can.
Yeah, I'm saying you have seen this question, right?
No.
As in, like you're trying this question only right now, no?
Yeah.
Number of divisors of n would be tau of n would be alpha 1 plus 1, alpha 2 plus 1, and so on. And this should be equal to 24, right?
Yeah.
Okay. So
Do I decide which one is smaller?
correct. So you have to think of 24, and 24 can be written as a product of 2 factors or 3 factors or 4 factors, right?
Yeah.
Suppose 24 was written as 24 into 1, right?
Yeah.
Then alpha 1 has to be 23 and this has to be 0, right?
Yeah.
So that would be 2 power 23, right? The number.
Yeah.
It could also have been written as 12 into 2, right?
So it's 13 and 1.
So it would be 2 power 11 into 1, 3 power 1, right?
Yeah.
Correct.
Yeah.
So you have to think of how can you reduce the size of this number. This is a very large number. This is also quite large number, right?
Yeah.
So it could have been 6 into 4 or 8 into 3, or these are the ways in which it can be written as 2 factors product. So in this 6 into 4 case, it would be 2 power 5 into 3 power 3, right?
Yeah.
And 8 into 3 case, it would be 2 power 7 into 3 power 2, right?
Yeah.
So you'll see that, okay, here 2 power 5 is 32 into 27. This would be 864, and this would be 2 power 7 is 128 and 9. 2 power, it is 1152. This is much bigger. We don't need to worry about it or this, right?
Yeah.
Now we should think of also ways in which it can be written as product of 3 factors, right?
Yeah.
So 24 can be written as basically 6 into 2 into 2, right?
Yeah.
Or 4 into 3 into 2, correct?
Yeah.
So if it is 6 into 2 into 2, you can get a number 2 power 5 into 3 power 1 into 5 power 1, right?
Yeah.
Then only the number of divisors would be this, right?
Yeah.
This is 32 into 3 into 5. So 32 into 15, which is 480.
This is smaller than the previous one.
It's smaller than at least these ones.
Yeah.
What about this one? This one will be 2 power 3 into 3 power 2 into 5 power 1, right?
Yeah.
That is 8 into 9 into 5, so
300.
360, right?
Yeah.
And what about 24 being written as 4 factors? You can write 2 into 2 into 2 into 3, right?
Yeah.
So the smaller number here would be 2 power 2 into 3 power 1 into 5 power 1 into 7 power 1.
Yeah.
So that will be 4 into 3, 12 into 5, 60 into 7, 420 again, right?
Yeah.
So now you cannot write 24 as 5 factors. You can only write this much.
Yeah.
So the lowest one is 360.
So Is it like the only way I can do it is to try everything?
This is a little trial and error type of question. There is no smart way to, without trial and error, there is not much you can do here. Right? That's
Yeah.
why they gave you a small number like 24. Otherwise, they would have given some big number, right?
Yeah.
The next one is not trial and error though. This one you have to think. Look at this. N is equal to P1 into P2 into P3. P1, P2, P3 are distinct prime numbers. If summation D divides N, D is equal to 3N, show that summation I goes from 1 to capital N, 1 by D I is equal to 3. So first of all, you have to understand what this part means. Basically,
Alright.
D divides N means divisors of N, right?
So the sum of divisors of n
Correct.
is 3.
Yeah, yeah. So,
Like di.
so this is DI actually. The same DI, right?
Yeah.
So you are given this, you have to prove this. And N is a product of 3 prime numbers. So what are the divisors of N?
1, P1, P2, P3, P1, P2, P1, P3, P2, P3, and P1, P2, P3.
Correct. Correct.
I know the last one is n. So the first 7 are 2n.
What? Oh, last one is N, you were saying.
Yeah.
You know 1 plus P1 plus P2 plus P3 till everything till P1, P2, P3 is equal to 3N, right?
Yeah. Yeah.
What do you have to find actually? You have to find this one, right? 1 by 1 plus 1 by P1 plus so on, right?
Yeah.
Till 1 by P1, P2, P3. This is what you have to find.
Yeah.
Okay.
Also, so I divide P1, P2, P3 on both sides.
Or you just add this by LCM. You can do that also. Just take common LCM will be P1, P2, P3 here, no?
Yeah.
And you will get on top P1, P2, P3 plus P2, P3 plus P3, P1 plus P1, P2 plus P1 plus P2 plus P3 plus 1, right?
Yeah. So and it's 3n.
This is equal to 3N and this is equal to N, right?
Yeah.
So it is obvious that, right?
Yeah.
So it's actually very easy question, this one, right?
Yeah.
There's actually nothing to do. You just have to just understand what it means. Correct?
Yeah.
Okay. Next one is this. Let f of n be the sum of number of divisors of divisors of n. So it's a little confusing, but think about it. You have to prove that f of 18 is equal to f of 2 multiplied by f of 9?
Well, let's calculate.
What?
I just calculate the F18 and
Correct.
F2n.
Yeah. You have to calculate and show. So sum of number of divisors of n, right?
Yeah.
So if you say F18, n is 18, what are the divisors of 18? Divisors of 18 are
1, 2, 3, 6, 9, 18.
right? So these are divisors of 18. What are the number of divisors of these divisors, right?
Yeah.
Divisors of 1 is 1 only. Divisors of 2 will be 1 and 2, right?
Yeah.
This will be 1 and 3. This will be 1, 2, 3, 6, right?
Yeah.
This will be 1, 3, 9.
Yeah.
And 18, we have already written divisors. It will be 1, 2, 3, 6, 9, 18, right?
Yeah.
So number of divisors of this is 1 divisor here, 2 divisors here, 2 divisors here, 4 divisors here, 3 divisors here, and 6 divisors here, right?
Yeah.
So f of 18 is coming out to be sum of the number of divisors. So 1 plus 2 plus 2 plus 4 plus 3 plus 6, right?
Yeah.
4 plus 4,
18.
8 plus 3, it is 18, right?
Yeah.
Similarly, what is f of 2?
2 is
Divisors of 2 would be 1 and 2.
yeah, and the sum is 3.
It would be 1 plus 2, right?
Yeah.
F of 9 would be, divisors of 9 would be 1, 3, 9. And sum of the number of divisors will be 1 plus 2 plus 3, right?
Yeah.
Which is 6. Correct?
Yeah.
So now you can show that f of 18 is equal to f of 2 into f of 9. Right?
Yeah.
Okay. Now, similarly, a different kind of function will be defined in the next question. So we will say define capital F of n to be equal to sum of all d which divides n and tau 3 of d, where tau 3 of d means is equal to cube of the number of divisors of d. Okay.
Yeah.
And you have to again prove that f of 18 is equal to f of 9 into f of 2. This you have to prove. So you have to first understand what this capital F is and then figure it out. So what are the divisors of 18? Let's figure out what is F18 first, right?
Yeah.
What are the divisors of 18? Again, 1, 3, 2, 3, 6, 9, 18, right?
Yeah.
These are the divisors of 18, right? So what we have to do here is f of 18 should be equal to tau 3 of each divisor, right? And add all of them, right?
Yeah.
Tau 3 of d, where d divides n, right? So
Yeah.
tau 3 of 2 plus tau 3 of 3 plus tau 3 of 6 plus tau 3 of 9 plus tau 3 of 18, right?
So yeah, so 1 plus 8 plus 8 plus 64 plus 27 plus 216.
Correct. So basically you have to figure out How many divisors are there for 1? There is only 1. So cube of number of divisors. So 1 cube. And this is 2 cube. And this is 1 and 3. So again 2 cube, right?
Yeah.
And this would be 3 cube. No, 1, 2, 3, 6, 4 cube, right?
Yeah.
And this would be 1, 3, 9. So 3 cube. And last one would be 6 cube, correct?
Yeah.
So this is how you understand this function. After this, you can do F9 and F2, right?
Yeah.
Okay. Then we can also look at numbers, which one special kind of numbers, which are called perfect numbers. What are perfect numbers? If sigma n of n, right? Sigma of n is equal to n. Now, not sigma of n, sigma of n minus itself, right? Okay, I'll just write it possible. I'll write it in words. If all the divisors of n except itself add up to n, right?
Yeah.
Then n is a perfect number, correct? This is the definition of a perfect number. So what does it mean? Sigma of n was what? It was sum of all the divisors, right? Including n itself, right?
Yeah.
So obviously, sigma of n includes n itself, and we are saying that these divisors should add up to n, right?
Yeah.
For it to be a perfect number. So you can say that sigma of n should be equal to 2 times n, right?
Yeah.
For a perfect number. Correct?
Yeah.
Examples are 6, 28. These are perfect numbers. You can check for 6. Divisors are 1, 2, 3, 6. But 1 plus 2 plus 3 is 6. Right?
Yeah.
Correct, no?
Yeah. Yeah. Yeah.
So similarly for 28 also you can check that. So this is the definition of perfect numbers. Now we'll try to figure out some properties. So one question that you should work on is this one. Show that n is equal to 2 power m minus 1 multiplied by 2 power m minus 1 is a perfect number if 2 power m minus 1 is a prime number. Don't try this now, try this at later after the class. One more question I will write. Capital N is equal to 2 power n minus 1 multiplied by 2 power n minus 1 and 2 power n minus 1 is a prime number. Also, 1 is less than d1 is less than d2 is less than dk is equal to n are the divisors of n, are the divisors of n. You have to show that 1 by 1 plus 1 by d1 plus 1 by d2 till 1 by dk is equal to 2. Basically, in this question, n has been given like this, and 2 power n minus 1 is a prime number is given, and these are the divisors of n. You have to prove this, right?
So like if I know the first question is correct,
Huh.
then this one,
Then
this
it is
one,
easy because then you can say that it is a perfect number, right?
yeah, then I do like in the same way as one of the previous questions.
Correct. So if you can show this, then you can easily show this because this type of thing we have done for perfect number. There was one question earlier, P1, P2, P3 question, right?
Yeah.
So try these two. We'll continue from this point tomorrow. Okay.
Okay.
Okay, that's all for now. Tomorrow we'll continue from here.
Can you make the recordings available to me?
Yeah, I will share the recordings for tomorrow.
Okay.
Yeah. Bye.
Bye.